Okay, hello. What I'm going to do, I'm already posted the final review for you that we are going to review it starting partly tonight. Okay. So study that one carefully. It's all power series and the polar coordinate that we talk about it, and I'm going to finish it tonight. So I finished the polar coordinate idea tonight, and then during the week, I post a couple of more for you, and I just go over that the final review. So the topics for the final are going to be the one on the review. Just focus on the power series because that's an important part of the calculus too. And the part about the polar coordinates, sometimes we don't get time to cover it, but fortunately now we got it. In case you want to take calculus 3, you need this type of ideas. Even if you don't, we give you enough information that, if you are measuring physics or some engineering discipline, so you have some idea of what's going on. So I've already talked about the idea that we did, the tangent line in polar form. Then we give you the arc length in polar form. And tonight I'm going to talk about the area under the curve in polar form. That's quite interesting one. And this is the one that we use in calculus 3 in 3-dimensional. Quite a lot, okay? And on the final, you will get we give you an equation in polar form to graph for us. Okay, then we give a problem of a tangent line to find the slope of a tangent line and determine when the tangent line is horizontal or vertical. Then we give you one problem on the arc length, the one that I did the other night for you. And then they're going to have 2 problems on the area and the curve. Okay, so it's like a 4 question from the polar coordinate. Then the other part are just like your quiz number 4, part of the test 3. I go over all of them for you and give you, then I will give you a worksheet for the final. Okay, so we didn't work any worksheet, and I posted for you, and the time is going to be the final day, and you can bring it back by the final, and we give you 10 points extra that I put on the syllabus for the worksheet. When it's a face-to-face, we give you the worksheet every week, but since we didn't have time, so I posted for you, then there's going to be a deadline, then it's going to be good for your final because the topic is going to be like the one that on the final, and it's good for you to do it and bring it back to get 10 points. Okay, I posted, and it's going to be called final exam worksheet. Okay, so it's going to be your job to get through this final, get an excellent grade in this course. Okay, 10 points extra. I posted. I try, and I've been doing my final at the university. I'm done now. So during the week, I get more time to post more solution to the final review for you. And then you can start looking at that final worksheet. I try to post it tomorrow for you. Okay, so it's going to be called final worksheet, 10 points by the final day, and very good for you to study that one for the final exam. Okay, so that will be 10 points extra. Okay, so let's go and take this one. It's quite interesting topics that we're going to cover tonight. Okay, if you practice, you'll be fine, and that'll give you a very good idea of what is going to be in part of calculus 3, or just, in physics, in engineering discipline. These are the type that we have. Okay, so we need to refresh your memory regarding what you did in calculus 1. Okay, for ordinary area under the curve, then we get it in the polar form. Okay, so the topic that we are going to cover, I can get a different color to write it down, maybe that's one. Okay, so what is the area problem? Okay, what's going to be area is not a good one, so I copy this one. Okay, that's it, the area of regions, bounded, okay, bounded by polar curves. Okay, that's the problem we're going to discuss. I just remind you what you did in ordinary function, then we are going to extend it to the polar form. Okay, recall that Remember, if y equal to the f of x is going to be a continuous function, on the closed interval, sorry, on the closed interval of on the closed interval a and b, then the area under the curve, we call it the area, okay, the area of the region, the area of the region bounded by, okay, bounded by the graph, bounded by the graph of function y equal to the f of x from x equal to the a to x equal to b is given by, remember the Riemann-Sam formula. The Riemann-Sam formula was a is equal to, okay, is equal to the limit of the sigma of f of ci delta x, I from 1 to n goes to infinity. That's, we call it Riemann-Sam, and that was exactly equal to the integral from a to b f of x dx. Okay, the idea was the idea of the partitioning, remember? So this was how we did it. So if this is going to be the area in question, the region, you see a to b, and this is your function, y equal to the f of x. What we did previously, we simply divided or covered it. We partition it first, okay? We partition in different parts, remember, we partition in different parts, and then we cover this area by some rectangle. These are the rectangle that we're going to make. Okay, so this f of delta x, you see this is if you take one of these rectangles out. So this dimension over here is going to be y coordinate of the point that we call it f of ci. And this part over here is just a delta x. So the area of one of these, okay, we call it ai. The area of one is f of ci delta x. Okay, the area of one of these, and since you are going to have, let's say, I equal to the 1, 2, up to the n, then we add them together. So the actual area is the limit of this ai or an when n goes to infinity. Remember, we're just going to make it finer and finer partition. We increase the number of the partitions, and eventually, you know, everything would be covered. And this would give you the definition of the integral. So the integral from a to b f of x dx. Okay, that's the ordinary one. Now the polar form. So in a case of the polar form, this is going to be our problem. Okay, so let's call it a problem or a question. The function would be changed, function y equal to the f of x would be changed to the function r equal to the f of theta. Okay, so the problem is going to be, would like to find the area, the copy of that problem, find the area of the region, let's say R, is time bounded. Okay, it's going to be bounded by the graph of, graph is going to be a polar form. You see, this is going to be the equation of the graph. R equal to the f of theta. Between, you need two numbers, but numbers are going to be rays. Okay, angles between the two Okay, this is going to be between two. Okay, it's going to be between two rays that we are going to have. Okay, they're going to be between the two rays, and that's going to be two values of the data equal to the alpha. Okay, and data equal to the beta. Okay, it's like, you know, the function that we did, we wanted to find between A and B. Now it's going to be between alpha and beta. Okay, of course, you know, as usual, we assume that the function is going to be assume that the function is continuous and positive. Data is a positive. For the area, you need to be positive because the area cannot be negative. A positive continuous. Okay, continuous function. Continuous function, or just, you know, that equation is going to be a positive continuous function. Okay, on this interval, alpha and beta. You see, if you graph it into polar form, this is going to be a situation you're going to have. You know, in the polar form, this is going to be, you see the x-axis, this is going to be the pole. So your graph is going to be something like this one. Okay, in the polar form, there's going to be a graph. So what we do, from the origin, we are going to get two angles. Okay, this angle here is going to be, okay, that's going to be your alpha. That will be denoted by data equal to the alpha. And then this portion over here, which is going to be data equal to the beta. Okay, this angle, this is going to be alpha, and this is going to be beta. Okay, the region in question, this is going to be the region in question in between. Okay, this is going to be the region in question that you would like to find the area of this region. So what we can do, we can get some rays. So this is going to be like, you know, this is going to be a curve. Okay, and these are going to be from these two lines, if you like, to rays, we call it. Now, if you partition it this time, this is going to be how you partition it. Okay, you partition it by getting different angles here. So you are going to have like a partition. You partition it like something with data 0, then we get a data 1, data 2, okay, up to the data n. So this last one is beta, and this is going to be your alpha, like the one that we did for the notion of the, okay, rectangle. Now, if you take this slice out, if you like, if you take one of these out, this is going to be the shape that we're going to have. It's going to be a shape of the circle. You see, there's going to be a circle. Okay, this is going to be a circle. And this is going to be the radius of a circle. You see, each portion is going to be like a sector of a circle. You see, it's going to be a sector of the circle. So this is going to be between two values of this data that we get over here. Okay, so this is going to be something like, you know, we call it delta I minus 1, two angles, and it's going to be delta I. So what we're going to have, this is going to be area of a sector. This angle in between is the one we call it delta data, which is going to be delta 2 minus delta I minus delta I minus 1, like the delta x that you did over here. You see this length that you call it delta x. So in this case, each portion is going to be like an area of a sector of a circle. And you know that the area of a sector of the circle is A equal to the 1/2. This is in your calculus or pre-calculus 1/2 of, okay, that is going to be 1/2 of the data r squared. R squared. That's the area of a sector in a circle. And it's easy to prove. because the full area of a circle is going to be pi r squared. You see that's the pi r squared is the full area. So the portion of a sector that you're going to get, you see this sector over here. So the angle is going to be delta theta. If you go around the circle, it's a 2 pi. So the portion that we're going to see, this is going to be area of a circle. You are interested in the portion of this. What is that portion? The portion is going to be delta theta over 2 pi radian. You see, this is how to do it. And if you simplify these two together, so that gives you exactly 1/2 of the, okay, r squared d theta live. You know, this is the angle that you get, but the angle is going to be d theta. Okay, so for each of those sector that I created over here, the area is going to be 1/2 of the r squared, and the angle is delta theta. Okay, so in the case of the ordinary function, you change it to the rectangle and you add the area of each rectangle, f of ci delta x. But in the case of the polar form, it's going to be just a sector of these curves, a sector of a circle. You see, the area of a sector of a circle is going to be 1/2 of the central angle. Okay, central angle, that r squared. The angle is going to be delta because it's going to be difference between two different values of the data or rays. So it's going to be AI 1/2 of the r squared d delta. Like here, you see, add them together, take a sigma, and change it to the new integral. Okay, so I go to the next one. So the actual area that you are going to be interested in, you see, I write it down here for you. Okay, each portion, the area of each portion is going to be what? Is going to be 1/2 of the r squared times delta theta. This is going to be true for each portion, I equal to the 1, 2, 3 up to the n. So your actual area, like the ordinary function, is going to be what? It's going to be limit of the sigma of, okay, the sigma of these AIs. You add all these together, but okay, you let n goes to infinity. Those partitioning one. And so if you substitute, it's going to be limit of sigma 1/2 of r squared d delta. Okay, I from 1 to n and goes to infinity. Okay, that's going to be 1, but remember r is what? R is your function, f of theta. So if you substitute here, so the area would be the limit of the sigma of 1/2 of f of theta, okay, f of theta all squared times delta theta. That's, you know, I 1 to n and goes to infinity. So because this is going to be used for each of those, is delta AI. And in limits, this give you an integral. It's going to be integral from alpha to beta, 1/2 of the f of theta, d theta. Because this delta theta would be changed to the t theta, and this is going to be your function. So, sorry, there is a square here. So f of theta all squared. So that gives you a nice formula. The area under the curve, okay, in the polar form is going to be alpha to beta, 1/2 of f of theta all squared d theta. Or if you don't like this one, it's going to be a equal to alpha to beta 1/2 of r squared. Okay, r squared d theta. Of course, where r is equal to the f of theta. So we can write down in the function form or in this format. So this is going to be the area under the curve in polar form. Area under a curve in polar form. used quite a lot in physics, okay, or in calculus 3, quite a lot in geometry. It's going to be used, so you have to know the formula. So the function would be given to you, and you have these limits, and you just substitute, take the integral with respect to the data, and then you're done. So that's going to be the area and their and their one curve that we're going to have. Now we can extend it in calculus 1 if you have two functions. In your case, I think it's calculus 2 because sometimes we talk about it. But we covered it in calculus 1. I did cover it in calculus 1 in your school. So if you have two functions and you want to find the area between two curves, you just get the area of each and you subtract it. So it's going to be the difference, okay? So let's do that one too, then give you example. You should know one question. You should be able to do one with the area under one curve and the other one area between two curves. Two curves in ordinary this is f of theta. You're going to have another one called g of theta. So it's going to be 1/2 of f of theta squared minus 1/2 of g of theta squared, okay? But for ordinary function is f of x minus g of x. So let's give you that one too, and then we are ready for nice examples. So what's going to be the area between two curves? Area of, okay, this is going to be the area of a region, okay? Area between two curves, area between two curves in polar form. Polar coordinate, or call it polar form. Okay, so we need two functions. So this is it. Again, let R be, okay, be the region bounded by the region bounded. Going to be bounded by the graphs. Bounded by the graphs of two functions, of two equations. R equal to the f of theta is one of them. Okay, and R equal to the g of theta, the other one. Okay, bounded by this graph between, okay, alpha, theta equal to the alpha, and theta equal to the beta, means from alpha to beta, where of course these functions are continuous. F and G are continuous. As in calculus 1, you must know which one is going to be on the top because the difference must be positive. Continuous such that we assume that the f of theta is on the top. Not a big deal. You can go with the absolute value because the result must be positive. Okay, this is going to be the case for all, okay, for all data in this interval, the domain. If this is going to be the case, then the area of R, the region between two curves, is given by the difference between those two. So this is going to be the area this time is integral from alpha to beta, two curves. So 1/2 of the first one minus the second one. So it's going to be 1/2 times f of theta squared, the top one, minus g of theta squared. That's it, the data. So basically you find the area of each curve first and then you subtract it. Okay, you subtract it and it's going to be like, if you like, you see, we have two curves. This is one of them and this is the other one. So the top one is the F, the bottom one is the G, and we get two numbers, two ray. Okay, this is data equal to the alpha, and this is the data equal to the beta. And the area in between is this one, you see. So we find the area of the top minus the area of the bottom one. Okay. So this is going to be the area between two curves. So I'm going to give you example. The examples are very unique examples. And remember the curves that we have. We have the cardioid, circles, and roses. Remember the roses? The case that, if you have is coming with a sine and a cosine, depends on the coefficients. Let me just, give you an example, then I remind you what's going on. So these are going to be, the famous regions that we're going to be interested in. And we give you one from each. Then on the exam, and we ask you a very similar one. Okay, so pay attention to the following examples. You need an example to understand it and to be able, to take care of it, or these type of problems. So let's start with circles, because the circles are going to be easy case. Okay, so example. The first one, we want to find the area. Okay, find the area. Okay, the area of, let's say, of the right semicircle with equation r equal to 4 sine of the data. Okay, we talk about if you have sine of the data only or the cosine of the data, that equation would represent a circle. Okay, so briefly, you are going to graph it. You can use your calculator if you have a graphing calculator that give an idea, or otherwise you can graph it easily to get these numbers, the circle, or you can change it to replace the r by x squared plus y squared, as I did the other night, to find it. But it's not a big deal. We can graph it easily to get these numbers. Okay, that's it. Just a couple of numbers would make it. You see, if you replace the data by 0, you see, if this is going to be, okay, if this is going to be the data and this is going to be r, for example, if you replace the data by 0, r would be 0. So you start from here. Okay, then quickly, it's a circle. If you go to the pi half, for example, that give you the maximum. That give you 4 sine of the pi half. For sine of the pi half is 1, so that give you 4. So that's the radius. It's going to be 1, 2, 3, 4. You see, that give you a portion of a circle. Okay, that's going to be the 0. So the data that happened here is a pi half. You need this one only. Okay, so it's going to be semicircle. They ask for the right semicircle. This is going to be the right semicircle that you're going to be interested in. Okay, so your function is r equal to the, you see the function that you want to integrate is r equal to the 4 sine of the data, and your data would be between 0 and pi half. Okay, and you know the formula for the area. So the area is going to be integral of, you have to find the integral from 0 to pi half. Okay, 1/2 of the r squared d data, or f of data, it doesn't matter. You substitute, it's going to be, you can pull out the 1/2. It's going to be 0 to pi half. R is 4 sine, it's going to be 4 sine squared. There's a couple of integral from the past that you have to remember. Okay, 1/2, I substitute 4 sine of the data, then a squared. just do it step by step for you so that you know what's going on. So 4 squared, that gives you 1/2. Integral from 0 to pi half. 4 squared would be 16. That gives us 16 sine square of the data. You pull out the 16, so that makes you do the 16/2. Integral from 0 to pi half. Sine square of the data, d data. You must know the integral of a sine square and the cosine square. You know that it's a double angle formula. We did it at the beginning, so we know it. When we 0 to pi half, use the double angle formula. It's going to be 1 minus cosine of, remember, 2 theta over 2. It's going to be used quite a lot, so refresh your memory and integrate it. So pull out the 2, so that give you 8/2. Integral from 0 to pi half, and this would be 1 minus cosine of the 2 theta, d theta. So that give you 4, and integrate. Integral of the 1 would be theta. Integral of cosine is sine, so minus sine of the 2 theta divided by 2 to be evaluated from 0 to pi half. Okay, this is double angle formula that we use. Now we substitute the pi half first. It's going to be 4 times, so that would be pi half. Okay, minus, and this is going to be 1/2 of the sine of 2 times pi half. Okay, this is where you put the pi half, now minus 4, you repeat the data equal to the 0, 0, minus 1/2 sine of 0. Sine of 0 is 0, so the second one would be disappear. So for the first part, these two would cancel out, you get the sine pi. Sine of pi is also 0. So the result is going to be 4 times pi half. So 4 and 2 simplify, that give you what? That give you 2 pi. Okay, that give you 2 pi. So the area is going to be 2 pi. The area of that right circle. Okay. And you know that we want to do it by polar form, of course. But just you are not going to do it just for your information. You see a remark. Note that this is a circle. The equation is a circle. So you know that the radius of this circle was equal to the 4. So the area of a circle, what is that? So the area of a semicircle, the area, okay, of a semicircle, you know, the area of a circle is going to be pi r squared, is a semi, so divided by 2. So that gives you pi half times 4 squared. It's going to be pi half times 16. Okay, sorry, it's r. What's the r? R is not 4, r is 2, sorry. Okay, this was all 4. So the radius is going to be half. So the radius is equal to 2. So that gives you 2 squared, which is 4. So if you simplify these two, so the result would be 2 pi. So A equal to the 2 pi. But we just we just want to use polar form, of course. It's just for your information to see that that's going to be the same thing. Okay, so this is how we're going to find the area and their one curve for us. Okay. So you get the equation, this is the formula. You have to know the limit of integrations. The limit of integration was 0 to pi half. So it's going to be 0 to pi half. The formula is 1/2 of r squared d theta. So you're going to end up with the double angle formula, integral of a sine square and the cosine square. So refresh your memory. Remember, for the sine square is 1 minus cosine of 2 theta over 2. And for the cosine square is going to be 1 plus cosine of the 2 theta. Okay, so this is for the circle. Okay, you have to know for the roses. So for the roses, two cases that you have to know. So for example, they ask you, let's sketch this graph first. You see a sketch R equal to the sine of the tree data. You know, there's going to be a roses with 3 petals, and compute the area. The area of one petal. Okay. You must know how to graph this one quickly. Okay, it's going to be, the 3 is an odd number, so it's going to be, it's going to be a rose with 3 petals. And we will talk about it, we can guess how we're going to do it. This was some idea of the trigonometric function I told you the other night. The way you can do it quickly is you may think about it as in pre-calculus case. If this is going to be an xy coordinate, the period is going to be 2 pi over 3, 2 pi third. And you know that when we want to graph it in pre-calculus, we divide this one by 4. Okay, so it's a 2 pi third. We divided by 4, which is going to be 2 pi 12. 2 pi 12, and that gives you pi 6. That will help you. How we're going to know, how we're going to divide this one. You see, so your graph in xy coordinate, of course. In xy coordinate, this is going to be the graph. The period is going to be 0 to, okay. If you want to get one version of the, to see what's going on for your graph, okay. So it was a 2 pi over 3, which is a 2 pi third. Okay, the situation that we are going to have, you have to break it into the pi 6 to just get to read. Okay, because the 2 pi third is going to be what? Is 120, if you like. So the situation they're going to have, you see this is going to be, for example, 0. And if it is going to be the pi, we divide it into different parts. Okay, there's going to be the pi half. Since you get a pi 6 here, so this is going to be the pi 6. Okay. And this is it's going to be 30 degrees. Okay, 30 degrees, then we get to the, okay, to get to the to match. Okay, I need the pi 6, then the pi third. This is going to be pi third, if you like. Okay, so then we get the pi half. Then you continue to get to the pi. Okay, this is going to be 30, 60, 90. So this is going to be 120, which is going to be 2 pi third, 150, and to the pi, for example. You don't need it. I just give you an idea. It's a sine function. You know that the sine is going up, down. Then this is going to be down. Okay, this is going to be down, and this is going to be up, and then eventually we get this part. You see, this is going to be like 1, 2, 3 pedals. Okay, and then you want to know to get this. You have to know this range. How we're going to make those pedals, if you like. Okay, so basically, if you want to collect some points to graph it, that will help you. That this is going to be the data, and this is going to be your R, which is the sine of the 3 data. So this tells you that if you're going to be data 0, that give you 0. If you go to the pi 6, that give you 1. If you go to the pi third, that make it to the 0. That give you one of the pedals, okay? And then you can get the others as well. So this is the situation that you are going to have. So the situation is this is going to be 1, okay, 2, and the 3. They are symmetric. You see this first one. So we start from the 0, this part, you see this part over here, if you like. This is pi 6. This is pi 6, and this part over here is going to be pi third. So that will be helpful to get what is going to be, what is going to be one pedal. So if you want to get to the one pedal that is going to be here, so what you have to do is you have to integrate, you see, you have to integrate from 0 to pi third. See, because that's, you go from 0 and just come back. It's nice to know this, okay, because it's the limit of integration is the one that you have to find, okay? So go up. So they ask for the area of one pedal, and now we can find it for you. This is it. So your function is R equal to the sine of the 3 theta, and that's going to be your range. So the area under the curve is what? Is integral from 0 to pi third, 1/2 of R squared d theta. Your subset is going to be 0 to pi third, 1/2 R squared. R is sine of the 3 theta. It's going to be sine of the 3 theta all squared. D theta, the same integral. So you put out the 1/2, that gives integral 0 to pi third. And this is going to be the sine squared of the 3 theta d theta. Again, the double angle formula, that gives you 1/2, 0 to pi third. Okay, that would be 1 minus cosine of the double angle, which is going to be 6 theta over 2 d theta. Pull out the 2, 2 and 2 would be 4. So 1/4, 0 to pi third. Okay, 1 minus cosine of the 6 theta d theta. So integrated integral of 1 would be, so it's going to be 1/4. This is going to be theta minus integral of the cosine is sine. Sine of the 6 theta divided by 6. Then it's going to be evaluated from 0 to pi third. Okay, so that's 6. So it's going to be 1/4 times theta minus 1/6. The sine of the 6 theta, but to be evaluated from 0 to pi third. Substitute, if you put the pi third, that gives you 1/4 pi third minus 1/6, the sine of the 6 times pi third. Okay, that's one version. If you put the 0, everything would be 0. Okay, minus 1/4. That would be 0 and 1/6, the sine of the 0, which is 0. So everything would be out. This 6 and 3 simplifies, that give you sine of the 2 pi. Sine of the 2 pi is also 0. Okay, this would be the sine of the 2 pi, which is 0. So the only thing that you are going to have is 1/4 times the pi third. So the result would be pi 12. So the area of one of those pedals is going to be pi 12. Okay, this is the way you are going to, the way you're going to check these. Okay, so that was the case that we had. Okay, the case that this coefficient is odd. Remember, when it's odd, you get only 3 of these pedals. I give you one when it is going to be even. When it's even, you double it up. Study this carefully. This is the only examples that we have. We may change, the number of the pedals that we have, but you must know very much in advance the range of the the limit of integrations. I'll give you another one with the even coefficient. Okay, for the even coefficient, we are going to have this one. We want to do example. Find the area. Find the area. Area of what? Area enclosed. Area enclosed by one loop. One loop. Okay, one loop of the, in this case, of the four leaved rows are equal to cosine of the two data. Remember, when the coefficient is even, you multiply it by 2. 2 times 2 would be 4. So you are going to have 4 pedals, okay, for this graph. Again, you must know it in advance that the limit of integrations, it's very important for us to see when one of these loop would appear. Again, you can use some idea from your trigonometric functions. Okay, so the solution is going to be, you see, if you want to get a quick one, again, find the period. No, it's also polar coordinate. The period of a cosine is 2 pi. You divide it by 2, that give you pi. In trigonometric functions, so we divide it by 4, so that give a pi 4. So these pi 4, pi 4, pi 4, you see, this is what would happen when we graph it in trigonometric, as a trigonometric function in xy coordinates. This is what would happen. You see, if you want to have a period between 0 and pi, 0 pi, because the length is pi 4, pi 4, pi 4. So you divide this one by 2, that give a pi half, and divide this one by 2, that give a pi 4, 3 pi 4. You see the graph of a cosine, start from the top, 1, -1, and this is the graph of the cosine. You're coming down, you go to the minimum, you go to the intercept, and then you go to the maximum. You see, this is what would happen to it. So these are going to give you those pedals that you're going to be interested in. Sorry, it's divided by, this is pi 4, of course, pi 4, and this is 3 pi 4. This is 90 degrees, so that's 45, that's 135. You see, that will give you the idea of how we're going to get those 4 roses. You see, you get a pi 4 between the pi 4 and the pi half and 3 pi 4. So this is a situation you're going to have for the cosine. You have to graph these, okay, to get the idea. So they start from the 0 here. You see, you can guess what's going to happen to the first one. It's going to be the data, and this is your R, which is cosine of the 2 data. You see, you get it from here that if R data is 0, this is 1. When the data is pi 4, you get 0. When it's a pi half, you get 1. So you get back to the original one. So this is going to be a situation we're going to have. So at 0 is 1. You see it's 1. So this gives you the first pedal. Let's say it's going to be 1. Looking into the mirror, that gives you another 1. Again, you go up 1. That's 3. Looking into the mirror, that gives you the 4th one. See, quickly we can grab. You don't need quite a lot. You must know what will happen. You see, you want to get the area of one of these. Okay, so this is the one. So you have to check what are going to get for the bottom and the top. You see, this would happen as a pi 4. You see, so this is pi 4. And you want to get the bottom one. It's like looking into the mirror. And so that gives you negative pi 4. So this is the data equal to the pi, and this is the data equal to the negative pi 4. You see, if you move from negative pi 4 to the pi, you will cover this area that you have over here. Okay, so that's exactly what would happen to get this one. And you don't need anything else. You want to find the area of one of these. That's it. So the data is going to be, you see, so for one loop, you start from negative pi half pi 4 to the pi 4, and your function is r equal to what? Cosine of the two data. So now you integrate. The area is integral from negative pi 4 to pi 4. Okay, and that's a 1/2 of r squared d data. You substitute, it's going to be negative pi 4 to pi 4, and that's going to be 1/2. The function is cosine of the two data all squared d data. So this is going to be, you put out the 1/2, the integral is going to be easy all the time. It's a double angle. So that gives you cosine square of the two data, d data. Again, use the double angle formula, it's going to be 1/2 integral from negative pi 4 to the pi 4. You change this one into the 1 plus cosine of the double angle. The angle is 2 data, so make it into the 4 divided by 2 d data. 2 times 2 would be 4, so that gives you a quarter. The leftover integral of 1 is theta. Integral of a cosine is sine, but divided by 4. The sine of 4 data divided by 4 to be evaluated from negative pi 4 to the pi 4. Okay, so this is going to be the case. And so what we are going to do is we can find it if you substitute to get these numbers. Okay, and you get a pi 4, you substitute over here. Of course, you know, it's going to be symmetric. You get negative pi 4 to pi 4 over here. You can simplify it. You can change it to the 0 to, okay, 0 to pi 4 and double it up. You see this portion down here and the bottom one are going to be symmetric. So if you like this part over here, you can change it into the, change it to the 1/2 times 2 of integral from 0 to pi 4. Okay, and the rest that you have. Okay, and this is going to be 1 plus cosine of the 4 data over 2d data. Okay, you can go from this one and make it to the 0 to pi 4. Otherwise, you get 0 because the bottom, top, and the bottom would cancel out each other. Okay, so these two would cancel out. So you get a 1/2 only, 1/2. Now you integrate it. Now if you substitute, the leftover is going to be the, when you put the 0, everything would be 0. So we get only pi 4. So it's going to be 1/2 times pi 4. And this is going to be a quarter sine of the 4 times pi 4. Everything else 0. The sine, this would be 0. So the result would be pi 8. It's a very popular, famous problem that the area would be pi 8. Okay, so these are some small points, but very, very important one when you want to integrate. If you stay with the negative pi 4, then it would be the same. You get the same answer, even if you stay with this one. You can check it because the sine part is going to be 0. This data would be negative pi 4. Then, you know, both of them would be the same. You know, you don't have to, but we can try it later and show you. So this is the area at wonder curve. I'm going to finish it off tonight, but because the area between two curves is a little bit more tricky, so I post another one for you maybe tomorrow. Okay, just give it a little time. Just check this quickly to get the idea. Then I give you more examples and I cover the examples on the final review. But this is the area under one curve. The two curve one is you have to graph it first, okay, and find the intersection points. And we talk about it in another lecture, okay. Read this quickly, then we come back and we give you the example from the review. The examples are very unique. If you know a couple of them, then you'll be fine. So check the one that I did tonight. If you have any question, email me, then I can explain it when I continue tomorrow. Okay, this week, every night I will post something for you to prepare you for the final. Okay, and check the final review. Do the part with the series that we did it before, but I'll go over the solution of all of them for you. Okay, have a good one and take care. Bye-bye.